Hello everyone and welcome back to this next part. So this will be what we're going to be building on today. So as you can see, this is where we left off. I have made some changes to the tent and now I can also move my units. Now this is very simple movement, very simple. There's no avoidance, there's no collision, there's nothing. But behind the scene it is using the navigation polygon stuff. So I believe I can go right here and show to you. Path is not going to work, but visible navigation I think it is. What we'll be building is this simple navigation polygon stuff that we're going to use to request path so our units can move. Now this is the foundation movement part of our units. There's no formation, there's nothing. We are just building the RTS from the ground up, so I thought it would be a good idea to make a simple system just to move units so we can get the ball rolling on getting the RTS systems going, and later we can also change the system how it works. But basically behind the hood it's just using the NavigationServer get path, so it's very simple, it's very fast. The debug for this is just a couple of spheres that I am creating, and this trail is also done by creating a lot of small spheres. So the blue ones, the light, the cyan color blue is where the points are. The green one is the physics frame of the units moving. The red one is the goal, and the blue dark one is on once it has hit a path point, is going to mark that for us. So let's see how we can do all that through code and advance our RTS project. So we are here on the panel here, and let's duplicate our last edited project so we can also work on stuff here. So I'll be calling this as our RTS tutorial, and this is going to be the part 3. So this does not follow the video parts, this is the project part, so these are different folders. So let's duplicate that and let's start editing. So I'm duplicating the last part, which I also have uploaded for YouTube members if you want to get access to the current project files. So there we go, this is where we last left off on the last part. We just made the selection system, and I think we also did the AABB selection. But as you can see, you cannot move anything. So let's go through one of the main changes before we even start working on it. So one of the things I change is also here related to the editor. So you can open the editor settings, and let's go to theme. And I believe here on base spacing it was about 5. And this is what it looks like, and I basically changed this to 1, so I got everything a little bit tighter so we can have a little more working space. It's a bit uglier, but I think it's more practical, so let's leave at that. The next one I'm going to also change is also here on editor settings, so let me show you that on here with the scripts. Let's go to the editor settings and let's find here on the script things. So I believe it's script list. And here you can have some options here for the editor, and the ones I'm going to change is to list script names, the ones you see here, as the parent directory and name. You can also do full path, and as you can see that is what it looks like. I'm going to change this to parent directory and name, because we'll be building more folders and stuff, and because more these assets have some name structure to it. So main is the main one for the object. If you just leave the name, and if matches conflict with the name, it's going to use the parent. So let's leave at default with the parent directory, so you can also see the parent directory before the script if it has any. So that's just for more clarity for the project. Also, I'm going to decrease the zoom here. We'll go back to 100. So what else did I change here? The base templates I'm going to also change to extend from RefCounted. And the reason for that is because it's going to require us to change whenever we extend from the project, because whenever I was using Node and I switched to Node 3D or 2D, I was having a little bit of conflict. So I'm going to leave this as extend RefCounted, so I remember that if I want to use this as nodes, I'm going to have to change that after we have built the script. So also the next one I'm going to change here is that you remember there were those type hints. So I think I'm going to increase this to 110, so just to help you with the tutorials. The other thing we're going to change is whenever we have type hints in the script, I'm going to replace this with script, because type hints makes less sense whenever we want to preload scripts as well. So we can do that simply by replacing all the files inside our project by going on search here, replacing files, and we can just say to find type hint and to replace with script underline. And let's also do match case in case if there's anything else. And once you click on replace here, it's going to access the folder and it's going to list all of the files that have these keywords. And these are the ones I want to switch to be replaced with underline, script underline. So you can also click here to see what there are. Now, once you do replace, there's no undo here. So be very careful when you are doing this type of stuff. So because our project is fairly small, we don't need to check every single one of them. We can just click here on the replace, and now our scripts should be a little different. Let's also close this, and here we are. So having script underline makes more sense than type hints, because this allows us to use script as type hints and also to call them whenever we want simply by calling this, and we can access the script codes itself. That's just something that I wanted to change here. I believe that's everything. So that's all of the big changes that I did to the project, and now we should be good to go to start working on the project. Let's just switch off this blue square here, which is the selection AABB, and I'm going to open the script of the unit and just leave here a reminder. So our object selection AABB, it's visible. Let's put in show. So whenever we want to use this code again, we also have here a reminder that it could be possibly hidden. Okay, I'm going to leave this AABB here because it's going to be useful for prototyping and stuff, but on the final release of the game, you probably want to delete that. Okay, back to here. Let's change the tents and start it by building our navigation polygon so we can start moving units. So the first thing we're going to do is to create a new node, which is going to be our navigation polygon, which is the navigation region 3D. And usually you put stuff under it to create a navigation mesh. So if I go here and say new navigation mesh, I can now start baking navigation mesh, but because there's nothing underlying it, there's nothing to be baked. If I put the grass here and the buildings and I click here on bake, you're going to see something very similar to what I did on the reference project, but we are not going to change the structure of these objects. Instead, we're going to use groups and stuff. So let's open our mesh, and under, it's not sampling, it is on, let me see if I can find, it's on geometry. So you can see here the source geometry for us to use when parsing the geometry or baking. We can switch this to groups explicit. And what this means is that it's going to use only objects that have been assigned to this group so we can bake the navigation mesh. And for now, we're going to use this. We can do this through code as well, but to keep the structure of the project as it is, I'm going to just use that. So now whenever I click bake navigation mesh, it's not going to work. And even if I put back again inside of the unit, it should not bake because it's using only groups. So let's undo that. And the way we're going to do now is to select our grass world mesh. And let me just minimize this. We're going to switch the tab here under nodes, and there's one signals and there's one for groups. And we're going to add here a new group. And let me just see what I called it on my reference project. So we're going to call this as RTS map, and let's turn this to be a global group. So this is not just some random group here. And we're going to say that for the description of this one, this is going to be, let's place here used for navigation. So something for us to remember what this group is used for. So now you should see this little icon here, which says that this node now belongs to this group. Now, unfortunately, you cannot select multiple objects to assign to a new node group, because once you do that, the inspector goes kaboom and says you can only select a single node to add signals. So the way we're going to do that is to delete all the tent objects, select the first one, enable it as groups. Then we can later duplicate this one using Ctrl D, and we're going to just rotate and place it around So we can use that to create the mesh for the navigation and stuff. This also is going to look a little bit different from our reference project, but doesn't matter because this is the final file you're going to access to. I always delete the reference projects after we have done it with the tutorial part thing. So let me just place here, and I can actually create a new one here. Now, of course, we need to also change the tent scale, otherwise this is going to be used like some kind of stairs for the navigation polygon. We can already test this out by doing a bake navigation, and it should work. The last thing we need to do is to copy the name of this node group and place here under source group name for the geometry mode of the navigation region. So once you paste the name of the group you want to be baked and you click on bake navigation mesh, kaboom, we now have navigation mesh baked for us to use to navigate around. And as you can see, we have some little couple of issues. Let's just enable quickly here on the ledge spans, and you can see the description for what that does. And this is going to help us with the navigation baking stuff. It's going to eliminate some edge cases here. Now, this navigation mesh is horrible, don't get me wrong, Godot does this automatically, but ideally for the RTS, I'm going to be probably baking and making the navigation polygon itself in Blender using a planner tool and special modifiers instead of automatically generating through this. So we'll see how we can do that later. For now, this is just for the prototyping phase. I think it's good enough, but for my liking, it's not super efficient. Anyway, let's just save, and I'm going to show you why the navigation mesh quality impacts the navigation itself, especially with the optimization argument we can use later. So, alright, we are done with the navigation stuff. And the benefit of keeping it separate is we can also hide it and don't hide the objects inside, because otherwise if you put them inside here and you hide, it's going to hide also the other objects. Here's not hiding because the node is not a visible instance. If I put this directly here, and there you can see that the tents are hiding as well. So let's leave this as it is, and I think I can also turn this off. The next thing we're going to do now is to create a collision shape for our terrain to be used for the mouse read collision. So let me open the reference project here. So the thing is, there is a static body 3D here that I think I can show you if I don't know why it's not showing up. I think it's because I'm not moving the ship. So as you can see here, there is a big square here for the world floor that it's being used as collision geometry for the mouse click. Because whenever you click with the mouse to move units, there's going to be a raycast from the camera towards the mouse click position. And this is not you cannot do this without any kind of physics. The easiest way for you to do that is just to use physics. So this is one of the uses of physics that I have not attempted to replace, because it works quite well for this. So basically we raycast from the camera towards the mouse position, and once we find a collision point, we're going to use that to move the units towards to. This helps us with accurate movement whenever you have mountains and stuff. So as you can see, whenever I right click, it does that. So we are going to build that inside of our project here. So it's simply the matter of creating a static body 3D, and we're going to give it a shape, which is going to be as simple as a cube. So let me see, collision shape 3D. This is going to be used for the static body. Let's create a new shape of a box. And I prefer box over planes because I have some issues with collisions using mesh, using planes as collision mesh for the floor. So I'm going to use box instead. And I think this terrain was 120, something like that. Maybe it's a little more. I don't remember the extension of this. It's probably 300. Yeah, something like that. So because I changed this, there's going to be some issues. So let's undo that and let's do it. So it's 250 by 250. And for this size height, I'm going to shorten it a little bit. So I get a little bit closer here, the collision shape for the terrain, I'm going to have like 0.1. So very close to the floor. Now we already have something to collide against the mouse, which is neat. So now I think we can finally hide this stuff. So now we have that. Now I think we are ready to start working on some code. And let's go towards our units, I believe. So let me see here. So for our units here, I'm going to start working on it. Let's start by adding here a constant for the movement speed, which you can control later. And this is probably going to be a variable for now. For the prototyping, this is a simple constant. The next one is going to be a var for the path. So this is the variable that's going to contain the path array. So this simply means that we have a packet, we have an array of vector trees which are neatly packed as for efficient memory. You can see here the definition of what these are. The next two vars is private vars, so you control the units. We're going to need to control at what path index they are, basically what path point, and also we need a boolean to control whether or not we're going to be moving the units. Later we're going to replace all of these move to path booleans with a AI finite state machine so we can control units, but that's going to be a little more advanced. For now we just want to move a unit, so let's use move to path. Next, I believe we start working on the functions, so let me just copy here the functions. So we're going to have a function here for the once we add a new path. Now there's something here that I want to show you. So you see that on my code I have globals.create debug sphere. This is what generates the sphere you saw here on the reference project. So whenever I want to debug the path movements of the units, I am generating those spheres. These spheres have been stored inside the Autoload. Autoload is basically a global script or node you can add to the project. So on the project settings, you can see here on globals, I have a globals, which is a simple script. So this is for us, is very useful for us to store global functions we want every object to be able to access. So we're going to do that very quickly here. We're going to generate a new script file and we're going to place inside a new folder. And we're going to call this as Autoload. And this is going to be called as globals, because just calling it global, I think I will have issues with conflict names, because global is a generic path name that Godot may use later. So I'm going to stick with just globals. So we are extending from RefCounted. Let's also change that to extend from node, because we need to add a node instance to our root scene to be the Autoload to be accessible by other nodes. So we need to be a node, another RefCounted object. Let's go now toward our project settings for our project, and let's go toward globals and grab here our script. So we're going to grab from Autoload our global script file, and we're going to be accessing that object as being called for globals. So let's add, and now this will be added to the project whenever we run it. So I believe we can already test this. Whenever we run the project, and I'm going to exit our scene, I'm going to see on remote here we have a node called globals, and this is the one we added through the Autoload. This is not part of our main scene here, as you can see. So we're going to have now this method here inside of our globals. So let's go now to the code of our Autoload, and I'm going to grab the part of the code here that creates the debug sphere. So it's going to be simply a function that does this, and it's a little bit extensive, but it's very simple. I'll show you what that does. So here, as you can see, it's a function that returns void and creates a debug sphere. We're going to have the first argument being a node, and we're going to be asking for a position to place the sphere, a time to delete the sphere, and a color to change the debug of the sphere. So we are going to generate a new mesh instance for every single call of this function. So this is not optimized, but it's just useful for you to debug prototype stuff, just as I am doing with debugging the movements of the units. So I'm going to generate a new sphere mesh for every single one of these objects. I'm going to set its rings to 1, its radius segments to 1, its radius and height, as you can see here. Next, I'm going to assign this sphere mesh back to the sphere as its mesh. As you can see here, I'm going to also scale the sphere mesh instance by the time. Now, this is something I like to do so we can have the little size of the debug sphere. So if I run my project here, you're going to see that spheres that are quickly to be deleted are smaller, and spheres that are bigger, like the red dot, which represent the path end position, are a little more bigger. So this is what this code does here to scale the sphere based on time. I'm going to be generating a new material for every single function call. So yeah, very expensive to run this. And I also believe I forgot to set the type here, which is a simple standard material 3D, and that should do it. So we set its albedo to the color argument we passed. We set its transparency mode to be able to use transparency. We assign that back as material for the sphere. We set its position back to the position argument, and we also now access the node that called this global function here, and we're going to use that to add to the roots of the scene as child. And we are also going to create a timer and connect its timeout signal to a blank new function here, which is going to simply delete this sphere once the timer runs out. So we connect the timeout signal. The create timer function belongs to the tree of the scene tree and basically returns a new time scene, a scene tree timer to be automatically freed once it's timeout. So very useful for you to do this kind of stuff for debugging. So now that we have done this, we can now create debug points inside of our code so we can see visually on our scene whenever we want to debug a position or coordinate of something. This is the code that we are doing right now. So here we have done the autoload for the globals. Now let's go back to our units. We have here a function for the new path, which is going to ask us for a position to move our units. We're going to change that position y to be equals to 0 because currently the navigation is floating above the ground because of a property here on the agent height. It's somewhere along these lines. I think it's cell height, as you can see here. And I don't want to reduce this property because, as you can see, it gives a little bit bugs here, and I don't know exactly how to fix that. So I'm going to stick this one to 0.25 as the default value and use this for top-down coordinates. But this is something we will have to worry about later as well, not just for now. So that is why I am setting the coordinates for whenever we pass a new path to our units to be equals 0. So we are going to change that as well. Here's the point where I randomize the movement of the units, because if I don't randomize, they all will go through a single point. So in order for us to keep around spread out movements, I'm going to use that. And here we set up the path. So this is where we generate our path. So we access the NavigationServer 3D and we ask it for a simple map get path. Now this returns the navigation path to reach the destination from the origins using navigation layers. So this belongs to the NavigationServer 3D, which is a server interface for low-level 3D navigation access. So this is how we are moving our units. We're not using navigation nodes and not other systems as well, just using this. And I think using this is the fastest way in Godot at the moment to generate paths using the navigation polygon. So for the arguments, it asks us for an RD, which basically is what is the navigation map RD, which you can do by getting the world 3D and get the navigation map and return us with the RD, as you can see here. And the second argument is where is the origin point, so where we want to start calculating the movement. It's going to be for the global position of the unit, so we pass its global position from the basic unit, and where is the goal of the path, so where we want to move the unit towards. And this is where this function argument comes into play. After we have randomized its target position and set its y to 0, we're going to pass that to the navigation server to say, hey, generate a movement towards that position. And this last argument is whether we want to optimize the path or not. And I'm going to show you why this is very powerful. This argument here is going to change how your navigation works. Next, we're going to change the current path index we have for our units to be equals to 0. and we're going to say to our boolean that we should now be able to start moving towards a path. Next, we're going to create the debug sphere points. So we want to create one for the goal of the path. So our where2 argument is going to have a debug sphere for it being red, and for every single point inside of our path, we're going to create a debug sphere of cyan color, and that is what this function new path does. Now we need a function to actually make the units move towards the path. This function just generates a new path and assigns back to our units. So now this is the code that actually moves the units. It's also very simple. First, we check if our path size is equal to 0, and if that's the case for a invalid path or a path that has been deleted and we still want to move, we're going to set its movements to be false and return from the function, so we don't continue to try to move. If that is not the case, if we have a path that size is not equal to 0, we're going to continue the function here. So first we need to ask where is the next path point, which is equal to our path point and the current path index. So this is the part of the code we're going to check that. Next, we're going to set the next path point coordinates y to be equals to 0. So we are going to stick it under plane here. Next, we need a direction to make our units look towards and to also move the point. So we are going to pass for our next path position minus our global position normalized. This is going to return us for the direction to the next path point. Here I'm going to generate a new debug sphere whenever we are following the path. So the trail you saw on this sample project here, these green ones is the ones being generated on this code. So here you're going to see the way we're going to create a new debug sphere once every we run this function at the current global position. Next, we're going to actually move the unit. So this is the part of the code that actually moves the units. We are just setting its global position to be added to the previous position plus this code here. And this is the direction to the next path point multiplied by our movement speed constant from the unit. And the result from this is just multiplied for delta. Next, we want to rotate the object towards the movement position, which is what this lookAt function does, which is a function for every single node 3D, and it has some issues, like we saw here on the debugger of the project with some coordinates being messed whenever you have one position over another. We are going to later redo this function to use a 2D coordinate top-down system, and we're going to use rotation math like a10 to basically normalize the rotation of the unit towards the next path position, but for now this should be sufficient for us to just make the units rotate towards it. It's the most simple way to do it. Basically, this rotates our units towards the next path point. Next, we're going to keep progressing towards the new path. So we move the unit to make it look to the next path point, but now we need to change it to move to the next path point. So whenever our global position distance squared to the next path point is less than 1, so basically whenever the unit is very close to reaching a path point, we're going to now change the current path index to be the next path point. So we change the index by 1, and we're going to create a debug sphere as dark blue whenever that happens. And if our current path index is, if it's higher or equal to our path size, that means we have reached the end of our path. We're going to simply clear the path. Once we clear the path, we should run into this issue here, and we're going to basically switch back to not moving the units. So this is basically what allows us to run the code. Now, for the code that actually calls the movement function is going to be just the physics process. So I'm not using the process function because the process function is going to run much more than just the physics process, which is capped to 60 FPS. So we're going to use the physics process for now. So whenever we have turned on the variable move path, we're going to start running this function here for every single physics process frame. And as you can see here, the follow path is the function we just took the explaining here. So doing this, we should now be able to move units using the path system. The last thing remaining for us to do is to generate the code for the player movements. So whenever we right click on the terrain, we now need to create the movement coordinate position for our units. So now is the moment to return back to our RTS player and start changing the code from here. And this is just the addition of a function here. We first need the method that's going to get the mouse collision points on the map. So here on the public methods, we're going to add a new function here. And this function is going to return us a collision point on the map. So for that to work, we need a collision mesh to work with. That's why we created this static mesh here. So once we have that, we're going to use this function to return a collision point towards from that. So this function does not return any arguments because the position we want to return is from the mouse and we want to grab the positional point of the map. So this function only returns us the vector tree where if we have hit a collision point on the map. First we grab the mouse position, we grab a camera we're going to use to make the calculations, and we need a camera normal. This is basically where the camera is pointing towards. In order for you to calculate a intersect array for physics, so basically to create a beam that's going to detect a collision between a line, we're going to use this process here called physics ray query. And for you to do this, this is the method that actually does this. So this is a collision code that's actually accessing the direct space state, which is basically internal physics of the Godot, which basically allows you to directly access the world physics 3D space state. Basically, we are saying that with the physics 3D of that current frame, we're going to be creating an intersect ray, which is basically intersect ray in a given space, which allows us to return an object with a dictionary which have the information we need for the collision information. Most precisely, the point where the collision happened. So we have to generate a query physics parameter 3D, which is basically the requirements for the ray calculations to work. So this is for usage with the physics direct space 3D intersect ray function. These are basically parameters you have to set up the intersect ray. So basically we generate a new query one and we want to start that line collision from the camera global position, and we want to point that beam of collision from the camera global position towards its direction multiplied by 1000, because the direction of the camera is just a small vector. Is a vector, I believe it's normalized by 1 and it's very short. It just represents where the camera is pointed towards. We multiply by 1000 here because we want to extend that very short ray to be actually big enough to collide against the terrain floor. Otherwise, it's not going to work. That's why we multiply by 1000 here. Next, we grab that, we are going to actually do the collision check. So we access the camera to grab its world state, access the direct space state collision stuff from the camera world space 3D, and we finally do a collision check using intersect ray, which is basically a ray cast internally used by the collision physics. Next, we're going to say if we have a size. So the collision function returns a dictionary with this information if it has collided against something, because if it has not collided against nothing, it's going to return a blank dictionary. So whenever you do this, we say that if we have collided with something, because we are checking if the collision dictionary has a size, and the only way it's going to return us with a size if it has hit something. Then if that's the case, we're going to return the collision position, which is the return method we are going to use for this function here. So it's the return result from this function. If that is not the case, we have read nothing, we're going to return this as vector3 0. And this is going to be useful for us to say that we have clicked somewhere in the map that we have not found a place to move our units. So now the last thing for us to do is to access the player interface inputs and say that the player right click on something that we want to start actually moving the unit towards. So we're going to do this function down here. And this is the function. If we have a right click somewhere, we're going to check if our player selection size is higher than 0, otherwise we're not going to try to move any units. And if we have a selection of even a single unit, we're going to try to move the units towards the mouse. This is the function that's going to move them, and I'm going to also show you here what that looks like. And this is also a public method. So this is just going to move the units toward the mouse, so the current selection of units. First, we're going to grab the collision on the map by requesting a position for div from the current mouse position, which is going to return the position if we have a collision. If the collision is not on vector 3, 0, which means that we have an empty collision, then we're going to actually move the units. And we're going to access for every object inside our player selection and request them from start moving by generate a new path. And as you can see here for our basic units, the new path is the function that we're going to start to move the units itself. And I think I'm going to change this code here. So this function is not actually update the selection drag box anymore, it has grown. So let's change this to be updates layer inputs. So there's a lot of things happening here. Let's just update this to be a little more clear what it does, because currently we have moving units, selecting units, and now we have this bit of code there. So this is all the code. Now we should be able to start moving units. So let me run our project and see if we have run into any issues. So we select, and I cannot right click on nothing. So we seem to have been missing something here. And now we need to start to debug this. So I don't know exactly where the issue is. So I'm going to do here the print to move. So let's see if we are actually calling the move function, and we are not. So as you can see down here, we don't have this print statement. So something here is not working. And let's see if I have that input on the input map. And we do have it. And I don't know exactly where the issue is. Player selection is not being higher than 0, it seems. So right click. So let's just see if that works. And no, that is not working. So we have an issue here. And it's because I have put inside of the indentation. So here you can see that's because of the indentation, I'm placing this bit of code inside this bit of code. So this is going to only happen if this happens. So let's deduct this, and now it should be ready to roll. So now only if the inputs here have been assigned, yeah, now it should work. So as you can see, that is how you can debug a code line. And as you can see, everything works just like this simple project. So as you can see, we can now move units. The last thing I'm going to do is just to change the tent objects. So I don't like their size. I think it does not represent the building anymore. So let me change this to 4, 4, and 2, or maybe 6, 3, and 6. Let's select all the tents. Let's move them up a bit. And let me just now space them a little bit. And we should be able to generate a new collision. The idea is to use this kind of system to also, whenever the player builds new buildings, I think the size is even bigger than the sample project, but no worries. So if I turn the collision, you're going to see that the navigation stuff has not been updated. We're going to bake it again. And there we go. Now we should be able to roll. So now we should be able to select units and move them along our buildings. So hopefully that was not too hard for you to follow it. There's a lot of code explanations, but as you can see, it now should work. So the one thing I'm going to show you the next is with Debug, and I'm going to say enable visible navigation. And here you should know it's not navigation. It's because my navigation polygon is turned off. So there was an argument for the navigation server that I want to show you. So you're going to see that the path points being generated are following the lines of the polygon. So this is an optimized way. If I go back here to the function that generates a new path inside of our basic units here on the navigation server function, this argument here where it says optimized is very important. If I put this to false, you're going to see that the mesh geometry is going to impact how it generates the mesh for the navigation stuff. So if I right click here, you're going to see that the units now take the middle parts of the polygons in order to move. And that frankly doesn't look worse, it looks quite better. But wherever you have these big splits here, you're going to see that's going to make the units move all over the way until it reaches the middle point and it can use it to navigate. So this is a limitation of the navigation server, and as you can see, for this type of baked mesh is going to have these issues where I right click here, it's going to move all of the way here on the middle parts of the mesh to go back here. If, however, you leave this as optimized, this is not the case. And this is the result of the navigation you'll have. So wherever you click here, it's going to optimize to move towards that. So you're going to see that just by changing an argument, and this navigation mesh is going to have different effects for the navigation itself. So this is something I want you to test on your navigation mesh as well. Now, I had some better results leaving that as false, but for this type of mesh, we're going to leave it as true to allow it to be optimized. The last thing I want to show you is that you can now basically also comment this by pressing Ctrl-K, and I randomize the movements to avoid this issue here. So let me just disable the visible navigation stuff. So let me also hide it from the region here. Let's run the scene. So I randomize because otherwise the units are going to stack together, as you can see here. Because there's no collision avoidance, this is what happens. So the units will stack one along the other, and it's going to be quite messy. Now, in order to avoid that issue, I'm going to simply randomize here a simple coordinate based on the size I want here to simply split the units along the target path. Now the system is using individual navigation path for every single unit, but it's just basically to move units from this prototype for now. Later I will be doing some type of formation for our units to not have this issue here, and even possibly we can work on something like units avoidance system using vectors. Nothing related to collisions, because I want this to be performant enough. So I think that does it for this tutorial. So this is not the final action, it's just some we're going to use as debug for this. Lastly, you can also comment all of these functions that creates globals. So all the functions that creates the debug spheres to hide those points. And now we have the navigation without those debug spheres. So that is just to show us what is happening behind the scenes here. Otherwise, you have no visual clue here. So that is all I have for you. Hopefully you have enjoyed. Subscribe, like, and comment if you have any questions. And we continue to build our RTS project here inside of Godot. I'll see you on the next part. So thank you guys for watching.